Yes, what we have is stratified analysis and logistic regression. So what we'll do, the first day will be on stratified analysis, while the last 2 days will be on logistic regression. So today we tackle stratified analysis. And well, I don't want to waste time asking for, since we have discussed, at least interacted, we have broken the ice. So I don't want to waste time asking for your expectation. Of course, I know you have expectation. There's one person that came in and I didn't see again. It's Dr. Fatima, and I think he's in AKTH Teaching Hospital. Aminu Kano Teaching Hospital. I saw her, and maybe the network took her out when she appeared again. And somebody also, another person may join us. Dr. Babagana, yes, I think he has joined now. Dr. Babagana Bako. So I think he says he's in Gombe. I used to think he's in a University of Maiduguri Teaching Hospital, but he's in a tertiary hospital in Gombe State. So Dr. Bako, introduce yourself because we have introduced before you came. Analysis. Today, tomorrow, we'll be looking at logistic regression. Tomorrow and next tomorrow, we're looking at logistic regression. So you may wonder, if you remember when we started the last 2 weeks, or 2 or 3 weeks ago, when we treated linear regression, we did it together with correlation. So we try to match correlation and linear regression to make one workshop. You know that correlation is related to linear regression. You may think, how is stratified analysis related to logistic regression? Somehow they are related because you'll be talking of odd ratio throughout both, and it's the same solution. So you know, they are trying to provide the same solution, just like the way we compare ANOVA and linear regression. It's the same thing with stratified analysis and logistic regression, because ANOVA and regression are virtually the same, and it's a matter of time the ANOVA will give way to regression, because what ANOVA will do, it is simpler to use regression to achieve and do better. So it's the same. You're going to see also that what stratified analysis can do, it is easier and better to use logistic regression to do the same. So 2 different analytic concerns motivate the division of data into strata, because what we're going to be looking at is stratified analysis today, and it just means division of data into strata. For example, if you can analyze now relationship between, the example we are having today, relationship between obesity and cardiovascular disease, you can just look at the analysis and say, oh, is there any statistically significant association between obesity and cardiovascular disease? You can even calculate odd ratio, which you are going to do to really know, okay, that maybe you'll be able to say that obese people are 2 times more likely to have cardiovascular disease than the non-obese people. You can do it generally, but if you want to do stratified analysis, you can, well, if these people, they are different age group, which you are going to encounter now, you can just divide them to 3 age group or 2. Okay, those that are less than 50 and 50 and above, and still try to find out the relationship between obesity and cardiovascular disease for group 1 and do it for the other group. In that case, you have split the data into 2 strata. You can split it to 3, 4. That is, you split it into strata defined by a particular another variable. That is what just means stratified analysis. That is, you split the data, you analyze separately for different classes or different strata. So what we are saying here now, there are 2 different analytic concerns motivate the division of data into strata. What motivated you to do that type of thing in the past? 1, the need to evaluate and remove confounding. So that there is something called confounding variable. You want to remove the effect of confounding variable, confounder. So it may make you to say, okay, you are doing stratified analysis. Of course, it is the same confounding also that logistic regression will do. Even linear regression is a confounding. It's only that in linear regression, the outcome is continuous, while in this case, the outcome is categorical. The other one, the outcome is numerical, while here the outcome is categorical. Now, the second need is a need to discover and describe effect modification, because it might be a confounder. Another thing that can happen is what we call effect modification. We go to modification, we're going to look at what they really mean and how do we go ahead, and how intelligent people in the past try to provide solution to the problem. So stratified analysis or stratification is used both to control for confounding, discover and describe effect modification. And it requires separating sample into subgroup or strata according to the confounder of interest or modifier of interest. Now, just to give an example of confounders or anything that may serve as modifier also: age, gender or sex, race or ethnicity. All the social demographics, they are like that. Social demographic variable, social economic variable, they usually serve as either effect modifier or as confounder. And that is why any study you do, you just have to capture all those things, because somehow, even if they are not the center of your study, they have a way of affecting your study. And that is why we had them. They are potential confounders and effect modifiers. Now, let's quickly look at what does confounding mean. This occurs when a variable is associated with an exposure and it affects the outcome. So it's better put in diagram. We're going to be showing about 3 diagrams saying the same thing so that we can have mental picture. I'm going to see something that are constant about the diagram, explaining the same concept. So once you can put the diagram in head, it is easy to conceptualize. Now, look at this diagram now. We have exposure, this green box here. That is exposure variable. We are looking at a relationship between this exposure and the disease of interest here. So the relationship of interest is between this exposure and disease. That is like say, smoking lead to lung cancer, or OCP lead to varicose vein, and many things like that. So that confounder is a third party now. You will see the arrow that leads from confounder to the disease is one arrow. So the confounder also is a risk factor to that disease, though that is not what you are studying now. No, you can have risk factor, more than one risk factor, many risk factors, to a particular disease. But when you are studying one, but there's another one, there's a risk factor, but that's not what you are studying. Not only that one is a risk factor to the same disease, it somehow relates to the exposure you are studying. That is a confounder. You will see the arrow that goes in between the exposure and the confounder is two-way arrow. So you are not saying that confounder leads to exposure or exposure leads to confounder. They are just related. Let me give you an example. If we talk about drinking and smoking, if somebody drinks, now you want to see probability, study probability of smoking, you can be sure that smokers are more likely to drink than people that are not drinking. If you have a group of people, say these people they drink alcohol and these people they don't drink alcohol, you want to calculate the probability of any of them smoking. You can be sure that on the drinking side, you go to likely they are more likely to smoke than the people that are not drinking, because it's still substance use. Somebody that just takes something, and that is in form of you are using tobacco or you are smoking or you are taking alcohol. The same thing, if somebody smoke or take tobacco, you want to see probability, you want to compare with people that don't take tobacco, you want to calculate the probability or try to look at the probability of taking alcohol or drinking. The people that take substance, smoke or take tobacco are more likely, the probability will be higher. So somehow, the exposure and the confounder, they are related. Not that one lead to the other. That is why the arrow is usually in the two way. But from the confounder to the disease, it shows that is a factor also. From the exposure to the disease, the exposure is a factor. The confounder is a factor. But the exposure and the confounder, they are related. If let's say the variable that is serving as a confounder is your variable of interest, the exposure, that one that is serving as exposure also may serve as confounder also. So when we talk about exposure and confounder, both of them are covariate in the sense that both of them are independent variable. There is only that one you call exposure is the one of interest now you are studying now. So the other one that may be potential risk factor, they are confounders. They may serve as confounder. Now, I think now there's one statement, the second statement, but it is not an intermediate link in the chain of causation between exposure and outcome. What it means is that confounder also leads to the outcome and it's related to the exposure, but it's not an intermediate link in the sense that it's not that the exposure will lead to confounder and confounder will now lead to the disease. No, because if that is the case, it's not a confounder then. That is, if somebody maybe is drinking will make you smoke, and when you smoke, it is the smoking that will lead you to the heart disease or the disease. So that shows that automatically if somebody is drinking will eventually smoke, and this one, no, that is not that. You know, there are some things there in the, maybe one condition will lead to the other, and this, like now, something that will lead to hypertension can lead to atherosclerosis. So all those things, if one thing lead to the other, they are not confounder. It's just a part of the causal pathway. The in confounder is a separate factor, but somehow is also associated with the exposure of interest. And if you look at it very well, if you remember the statistics when we were doing linear regression, and we are going to talk about it here also. We talk about multicollinearity. When sometimes two factors, if they are related like that, they will correlate very well. So multicollinearity, if two factors correlate well, of course, they will be serving as one. So it's part of the condition when you are running your multiple regression. You don't put two factors that correlate perfectly, like up to maybe 0.9 and above. Don't put them. So let's move forward and proceed. The next slide now is giving an example. This is an example. You see, this one is looking at the relationship between coffee drinking and heart disease. And the third party there is tobacco use. If you look at it, the horizontal arrow is the one that moved from coffee to heart disease. That is the relationship of interest in this one. Now you will see that a confounding variable is the tobacco use. And this tobacco use, one arrow go to heart disease. It means that it's a factor for heart disease also. But if you look at it, there are two arrows, just like the other one. There are two arrows, one arrow from confounding to exposure, from exposure to confounding. Both of them, they are related. So you cannot say one caused the other. They are just associated, somehow. They are associated. Just like what we said before. Both of them are substance use, coffee drinking, tobacco use. People that take tobacco use tobacco. If somebody is using tobacco compared to somebody that is not using tobacco, who will likely take coffee? Yeah, you will see people that take coffee, they don't use tobacco, but if you put people that use tobacco and people that take coffee together, I try to see which one will likely, people that take tobacco rather, and people that take coffee, and people that don't take coffee, who will likely use tobacco? If people that take coffee, it's the same thing. People that use tobacco and people that don't use tobacco, who will likely take coffee? So they are related. And you see, it's not an intermediate, it's not as if maybe when you take coffee, you now use tobacco will now lead to heart disease. Both coffee on their own and tobacco on its own lead to heart disease. And you are interested in studying coffee, so tobacco is a confounder. If it is tobacco, you are trying to study the effect of tobacco on heart disease, Yes, coffee also will be a confounder. Look at this third one. Relationship between alcohol use, lung cancer, and third variable, smoking. The same thing. If you look at, you are studying alcohol, how does it lead to lung cancer? Now, smoking is there. It also can it's a risk factor for lung cancer. The smoking and alcohol use, they may be related. Look at it. You will see in the theory diagram I discuss now. You see one arrow will go from the exposure to the alcohol, another one arrow also from the confounder to the alcohol. Both of them equally lead to the alcohol. But the arrow that moves in between the exposure and the confounder, they are two-way. It's not a causal arrow. It's just an association that both of them, they are related. That's what it means. Now, if you want to remove this confounder, what do you do? What you do, there are things you do to, if you want to study and want to remove this effect of confounder. Because somehow, the effect of it is that if you don't do as if they don't exist, you will end up saying, oh, alcohol responsible for lung cancer. Can you see the odd ratio is 20? You that take alcohol are 20 times more likely to have lung cancer. Whereas most of those people that are taking alcohol you have recruited, they smoke. And smoking also contributes. So some of those 20 times you are talking of, maybe smoking is contributing up to that. So in that case, smoking is a confounder. It marks the effect of the two. So it may amplify or reduce. The confounder can amplify. But in this case, it's going to amplify because you are looking at the effect of alcohol on lung cancer. The smoking also contributes. So it will give impression that, wow, alcohol is doing well. It's really causing lung cancer. But whereas maybe smoking, was it last week? Okay, I was discussing when I was giving an example. Because the example you encounter may not be smoking and alcohol. I said somebody was trying to look at knowledge of depression. Depression, is it postpartum depression among women? So he realized that the knowledge increase among the higher the social the level of education, the higher the knowledge. You also see that the higher the age, the higher the knowledge. You can see that age and level of education, they confirm. Both of them can confirm for one another. By the time you start to look at age, how age affects the knowledge, education is a confounder. By the time you are looking at how education affects the level of education, affects the knowledge, age is a confounder. Because somehow, when you are talking of about children of women of reproductive age group between 15 and 49, and you are studying if those people that are less than 15, less than 20, 15, 16, you don't expect them to have even had tertiary education. Yes, if somebody is already a woman, giving birth at the age of 15, 16, 17. So when will you expect so you don't expect them. So you got to see that somehow, the level of education among these people may be related to their age also. The older may be more likely to have acquired tertiary education. So can you see? So if you are considering the effect of age on the knowledge, level of education is a confounder. If you are considering the effect of level of education on the knowledge, age is a confounder. That's an example. Now, how do you remove it? There are 5 different ways. And 3 of these 5 ways, as you can see, are employed during study design. At the inception, make sure you factor them in. And believe it or not, all those 3, they are commoner with experimental design. They are commoner with experimental design. Randomization, restriction, matching. Those things are commoner with experimental design, where the matching, you can also see in observation very well. You see that randomization is commoner with experimental. In fact, you see the hallmark of experimental design is randomization. So it is when, in fact, any experimental design that is not randomization, they call it semi-experimental or partial experimental. It's not the pure experimental design. You see that during the level, at the level of this study design, you can do all this randomize. Randomization just means by separating people into different groups, just by chance. So you do balloting. It's not because you know somebody. Whoever fall into any group, either control or treatment or whichever group, is just by chance. It's not because somebody knows or intentionally. But we know that the effect of randomization may not be felt on the study if the study sample size is very small. If the study is very large, by the time you are dealing with 400 people, if you are doing balloting, imagine you are studying this issue of you want to study effect of one on the other, or one factor on the other. Even if there is a confounder, by the time you are you are putting people into the two groups, 400 people, definitely into just by chance. You will see that whatever that thing is that may serve as confounder will have fizzled out, in the sense that it will be evenly distributed between the two. You won't see one group having that particular, all the people with that particular attribute to the detriment of the other group, because you just allow by chance. But that chance occurrence only works if the sample size is very large. If the sample size is very small, there's a tendency for one side to have one particular factor more than the other, which can serve as confounder. And that thing can amplify the effect or match the effect. For example, now, if you want to test for the effect of a drug, a new drug, and you, when you are selecting, you only select the few bad case to that old one, because you want the new one you want to have good result with the new one. And if the pharmaceutical company has already paid you, the results will come out well. So you can influence it. By the time you are recruiting the cases, the one that are worse, put them to the other side, that is the old drug. The one that are not so bad, put them to the new drug. At the end of the day, the new drug will appear. Those ones will receive, they will be well more. When you are measuring your outcome, all those variables, it gives the impression that the new drug is working because it's tilted to one side. But if you do randomization and the sample size is large, you may not likely both the worst and the good and mild cases will evenly distributed among between the two groups. But if the sample size is very small, even if you say you do randomization, it will be tilted to one side. It is when sample size is large that the thing balance up. So restriction. So somebody is making, I don't know, computer is making noise. Who is not muted? Okay, Dr. Gungbe, something is making noise from your end. Off your yes, thank you. So restriction is when you that factor, you say you restrict the factor. So you avoid recruiting anybody that have that factor. Like for example now, this issue of smoking and alcohol. You may say, okay, we don't want tobacco use, you don't want smoking. It's out of the game. So that is restriction. The matching just means that consciously, if you recruit one person that have one attribute, that particular confounder of interest, you to one group, you make sure that there will be corresponding person that have the same attribute on the other group, so that you cannot say that they cancel out. The number that have the attribute on one side is equal to the number that have the attribute on the other side. They already cancel them out. That is restriction. Matching, that is matching rather, matching. But sometimes when you have many confounders, it may be difficult for you to match. You match for age, you match for sex. Matching also may not necessarily mean that if you are matching for age, that will be exactly the same age, 35 years. May give window of 2 to 5 years. Okay, between, if the difference is not more than 3 or 5 years, you still say that okay, they are still the same age group. So now sex, we can easily match for sex, sex for sex. Then those are the 3 measures, and that's not what we are interested in now. The one we are interested in are these last 2. The method you employ during data analysis. And these are common with observational design, because observational design, you don't have opportunity to manipulate, to control the environment like experimental design. So in observational design, you try to remove this confounder from during analysis. And two ways of doing that. Stratification, that is, you split the group into different strata. You split the data set into different strata. Like for example, if it is smoke now, smoke and not smoking. So you analyze for people that are smoking, you analyze for people that are not smoking. But this one we want to do now. What we do, we're going to do, okay, obesity and cardiovascular disease. Since age is a risk factor, maybe a confounder. So age group less than 50 and 50 and more. So you have two groups. You now do the analysis separately for these two age groups. That is stratification. You stratify your analysis. So the last one is statistical modeling. So you try to model through statistical method, regression. That's all. Either linear or logistic regression. But here now, we'll be talking about logistic regression. And this is our workshop. So stratification, regression, you're going to see later that, well, the reason statistical modeling will just, even this stratification, how many people do you see do stratification? How many journals have you read now recently that they did stratification? You will not do, because it's becoming obsolete. What people do is to, it has given way to logistic regression. You do regression. What you will see in the journal will be regression. We discussed that one further later. Now we have looked at what confounding is and the way to remove them, because we are coming back and pin down on the stratification now. But let's look at effect modification, because this stratification is done because of either confounding or effect modification. So let's describe effect modification. Before we do that, I don't know if there's any question, because I usually pause, because you know that the question will not accumulate. Any question? Any question? No question. Okay, that's great. Yeah, Dr. Fatime. Okay, Dr. Balogun, you want to ask a question?
Yes, I've actually been trying to look at matching as it is.
Okay.
And even in experimental studies, I don't know, because sometimes, I mean, most of these journals will say the case was matched for age and sex.
Yes, that's why I said you match a lot, yes.
So,
I said something that those three first one, they are more with experimental design. Go on.
Okay. So, but for observational study, that cannot be. Are you saying that is not possible? So?
No, you can match. You can match in observational study. But it's only that what is commoner, the examiner. You can randomize also in randomization. Just means that you select into well, the observational. You can randomize because people do what they call it, comparative studies. Sometimes they want to compare, but most of the time, in observational study, you are studying people in their natural state. You are not the one that put them there, urban, rural. So you are not doing randomization. That's why it's commoner. No, the word randomization does not actually mean it's limited, but most of the time, it's experimental that does it. The restriction you can do in observational. The matching you can do it very well. But the statistical modeling and stratification, we do it more in observational than experimental. Not that they cannot do, you do it also, but it's more in observational.
Okay.
It's just a matter of what is, like for observational study people, they have not manipulated the environment. So they just have to use a lot of statistical way to control for confounder. Whereas for the experimental researcher, if he has manipulated very well, we just need simple statistics. You don't need much to know, because he has already controlled for all those things from the design stage. You don't need to do more statistics to bring out your result. And that is why in those days, the people that do experimental research, they do ANOVA a lot. They do ANOVA. why the observational researchers do regression. But all those who have now discovered that is the same. So just like the way stratification is giving way to regression, has given way to regression, ANOVA will still fizzle out and give way to regression. That's just it. Okay, any other one? Dr. Fatima, when I saw you logging in, later you log out again. So I don't know, you're the only one that have not introduced yourself since you came. We've done the introduction before you came. So are you there? You have to unmute yourself. We want to hear you. Hello?
Good evening, sir.
Good evening, yes.
Sir. Good evening, everyone.
Good evening.
Yes, sir. I had issues logging in with my internet.
Okay, sorry for that. Sorry for that. So we just want you to introduce yourself so that people just get to know ourselves. Everybody has introduced only that you think it is yeah.
I'm Fatima Carey. I'm a senior registrar in pediatrics at Aminu Kano Teaching Hospital.
That's great. You're welcome. Okay.
Yes.
Yeah, welcome. Now let's proceed. If there's no question.
So I have one question.
Okay, go on.
With regards to the matching,
Okay.
if you match a variable, can you measure that variable? Can you assess that variable?
Yeah, you see assess it. You see assess it.
Okay.
You can see put it because for confirmation. Like for example now, if you match for sex, so when you do it, they will expect that it's the same sex distribution on both sides. So if the male is 30% on this side, male should be 30% on this side, remaining female. So if you say you match and they see the result that is different, you have not matched. If you match for age, you know that the age may not necessarily be 1 for 1, as if somebody is 35, you must have on the opposite side 35 exactly. It's going to be difficult. So you may have a range of value that, okay, it should not be more than 3 years different. So when you now compare the age now, it should not be statistically significant between the two sides if you actually match. You understand me now? Even though you see some differences, but that's different should not be statistically significant. So if you don't capture that variable, how will you even confirm that you match? Yes, you must give information about that variable. I don't know if you are following me. Yeah, that's it.
Yes.
Like for example, in this case of you are studying relationship between coffee intake, heart disease, and tobacco use is the confounder. You now match for tobacco use. Of course, you'll be able to tell that for each of them, 10% of each of the two groups are tobacco user. To really say, okay, yes, it's cancelled out. We have equal proportion. But if you say you match, you didn't even tell us about the tobacco. There's nothing from you didn't tell us that how many people are tobacco user, how many people are not tobacco user. So how will you prove that you actually match? So I think we proceed.
Like,
okay, go on.
Sorry, sir. Like for the tobacco users, if probably you're assessing you have equal proportion on both sides, the tobacco smoke users and the non-users.
Yeah,
can you now say that gender or age with that outcome of
gender or
since
age?
you have matched it? Gender, sorry.
If you match the gender, right?
Yes.
No, if you look at it, most of the things you are matching, they are not even outcome, they are predictor. Because you have your outcome you want to measure. And there's a factor you have in mind that is leading to the outcome. And you are feeling that this particular thing you are matching for is a factor also that may be related to the factor you are measuring. In that case, you have to, if you do EK is not taken, it may be this other factor is the effect you are measuring without knowing. You will think you are measuring the effect of your own factor of interest. And that is why you are matching for that third factor. So both of them, they are not actually outcome measure. They are more covariate that they are exposure variables. So they are called them explanatory variables. Like most social demographic variables, like age, sex, they are. So what do you do that the sex is the outcome? Sex cannot be outcome because the way you are born, you are a female now. You are a female from is God that determined that. So there's nothing, there's no condition that lead to you being female. Is it you say that, well, they say how many of those, if you say that, like you're a doctor now, they say that, is it the doctor being your profession that make you female? No. But you can look at the effect of the female on the profession. Oh, okay, how many female are doctor? How many male became doctor? In that case, if you are looking at professional group and sex, sex will be exposure. The professional group, your profession may be an outcome because your sex may determine the type of profession you go to. But your type of profession cannot determine your sex. I don't know if you understand me now.
Yes, I do.
Yes, and another thing is that so that you won't be confused, a particular variable that is serving as exposure now, when you relate it to another variable, it may be an outcome. Then, for example, now when we talk about sex and education, level of education, sex will be an exposure, level of education will be outcome. But when you compare level of education and socioeconomic class, you may say level of education is an exposure, while socioeconomic class will be an outcome because your education will determine your socioeconomic class. It's not your socioeconomic class determine your education. So sometimes when to talk about outcome and exposure, it depends on which two variables you are comparing. But in a particular study, you have your variable of interest. You have one particular outcome variable, which is the particular outcome variable that you are studying. And that particular outcome variable is your research question. And you now want to know what are the factors that are responsible, that contribute. And those factors, whether you like it or not, they may be plenty. Those are the ones you want to be, it's among them also. Some of them will confront from one another. If you have many factors now, if you pick one, some other factor may be a confounder to the other factor. So some that's why we do multiple regression to remove, if any way they confound for one another. Are we together? And if me and you we are friends now, if me and you we are friends, we are in a class, we go for exam. If they give us assignment, if you know that particular subject more than me, you will be helping me. Anytime I collect the assignment, I will do it. I will add to my. So before you know it, I will be scoring high mark like you. But if they now if they want to remove your confounder, they put us in the same place in exam. Now, no cheating, no communication. Then you will know the person that is not so good to it. Can you see now? So that is the way the confounder works. Some of those few factors, you say they are factors. Someone they confound for one another. And your friend also that you are helping in one subject, you may be helping you in another subject. You understand me now? So if you are helping the person, to do the assignment in one subject, he's helping in the other subject the person is good at. But in both subjects, he's confounding, you are confounding one, he's confounding for you in the other one. So if they really want to know the effect, for all those two subjects, put it together in the exam and don't allow cheating. Everybody will score what is supposed to score naturally in this subject. I don't know if that one.
Thank you, sir. Yes.
Oh, you're welcome.
Can I also ask something?
Yes, sir.
Yes, sir. Sir, I think what she was, the way I understood that question initially, which me too, I wanted you to comment on it, is that, yes. For example, if you are doing the case control,
yes,
and you want to find out the impact of an exposure variable, and now you have matched the patient, the two groups, either maybe you've matched for age or social class. I think what she was asking, the first question she asked, is that since you have matched them, you are only trying to concentrate on that variable that you are looking for. You may not be able to analyze them because the two sides are the same. So I wanted to comment very well on that one because when there was a case, when we match them now, it's like you've already canceled that one out. So you are looking for those variables or one or two variables only that you are targeting. So you match the other ones. Can you still analyze? I think she was asking, I just wanted to comment so that I will learn more on that kind of
Yes,
situation.
the issue there is that the matching the variable does not actually the age you are matching. It does not remove the effect of the age. If you match age, it does not remove the effect of age from what you are doing. But what it does is to how age affect the other relationship between the other variable and the outcome. That's what it has removed. It has removed that confounding effect. The just like what the example I give also. If they try to I give you, I help you in some subject, you help in some subject in our tutorial, whatever, we score high. When it comes to examination, it does not stop each of us to be assessed, but what that examination, removing confounding, preventing us from cheating, what it has done is that it doesn't allow your information to be transferred to me. It doesn't allow my information to be transferred to you. So you only put in your information, the relationship between you and your outcome and your knowledge. So it doesn't stop you assessing age, what you have, it doesn't even affect the effect of that age on the outcome. But what it affects now, what it helps you remove is that how age will mask or amplify the effect of the other factor on the outcome. That is what you have. Let me give an example. You know, if when we talk about like case control, you are talking of now, or let's say case control, since you made mention of case control, you are looking at the effect of, let's say, varicosity and OCP among women. People that have been using OCP and people that have not been using it. No, you have two groups.
Yes.
The OCP user and non-OCP user. So you want to see the effect of OCP. The effect of OCP on varicosity. Varicosity is the outcome. OCP is the exposure. Are we together?
Yes. Yes.
Please, who is making noise? OCP. So please, Salu, please, we are making noise. Please, the two Salu, we have Shimeze, Salu, and Adaya. They are not supposed to be here because they didn't subscribe for the workshop. So, Salu, Dr. Adaya, you didn't subscribe for the workshop. Okay, let me just finish what I'm explaining. Now, when you are having that, if there's another factor which is confounder, let's say marriage, being married or not married, somehow, or something that is one factor or age or whatever that may be as a confounder. Now, what you do is that when you are analyzing, naturally you are supposed to analyze, just do your cross tabulation and say this is the effect of OCP. And we want to be able to say that why you have, since it's case control, why you have people that have varicosity and people that don't have varicosity is for you to know, to really see how many times the people that have varicosity are more likely to have taken OCP before.
Will have OCP.
They will have taken OCP in the past because it's a case control study. You start with varicosity, no varicosity, will have taken OCP. And that's why you take cases, people that have varicosity and people that don't have varicosity. So you look for the, begin to ask them questions about OCP in the past. You expect the people that have varicosity, if OCP is contributing to varicosity, you expect more of the people that have the OCP in varicosity to have taken OCP in the past. So if there is a confounder, what will happen is that the confounder will affect it may give impression that, oh no, people that have varicose, they are not likely, it may reduce the odd ratio or increase it. What you do in that case, that when you look for case that have varicose, you now look for, if age is a confounder, what you do is that if you pick somebody that, you get somebody that has varicosity 30 years, you look for somebody that doesn't have varicosity that is close to that age. That's what you do for each of all the cases of varicosity. You look for age match to cancel, because if you don't look for it, it will affect the varicose. You go to see when we demonstrate it.
Yes,
Exactly. But it doesn't stop the analysis, the effect of the age of varicose doesn't affect it. It's
Okay,
only
yes, I've
NPU
gotten
to
it. Doesn't stop.
yes, and yeah. So that is just it.
Yes, no, it's clear now.
Yeah. So the when I send something, there are some people here, Alimin, you are not supposed to be here. So those other people, they have logged out. Dr. Alim Hakim, if you don't subscribe, you are not supposed to be here. So let's continue. Now, let's talk about effect modification. Effect modification refers to change in the magnitude of an effect measure according to the value of some third variable after exposure and disease, which is called an effect modifier. Just in a simple way, it can occur when the relationship between one of the explanatory variable and the dependent variable is not the same for different level of other explanatory variable. Let me just give an example. The example we are going to use is obesity and cardiovascular disease. The obesity, we want to see how many times the people that are obese are more likely to have cardiovascular disease than people that are not obese. Age is it may be a confounder or effect modifier in the sense that age, you know that the older a person, the more likely the person will have more cardiovascular disease problem. So that shows that the people that are maybe 50 years and above may more likely have the problem more than people that are less than 50 years. So if it is a modifier, what will happen is that if you split your analysis, you look at the relationship between obesity and cardiovascular disease for people that are less than 50 years. And in the other group, you look for it for the people that are more than 50 years. You are split it, stratified analysis. The relationship will be different for the two age group. The relationship will be different for the two age group if age is a modifier. What it means is that if age is a modifier, that shows that for the effect will be different for the one that are less than 50, and the effect will be different for the one that are more than 50. That is what it means. Now, if you are going to see later, if age is not a modifier, if it is a confounder, when you split it, the effect will be the same. The effect of obesity on cardiovascular disease will be the same for the people that are less than 50 and the same for the people that are more than 50. So the effect modifier, what it does is that that third variable, it's as you are moving for different value of that third variable, it's changing the effect. Who is making noise? Somebody is making. You today, you are making noise. Please mute yourself. So let's just quickly. So when we use Martin-Hansen method to control for confounding, yes, where this slide. Okay. So the best way to control for, when you are controlling for confounding, the effect modification and confounder, they go together somehow, if you want to assess them together. It's the same, it's a step, 5 steps. The next slide will show you all the 5 steps. As you are following the step, you first of all eliminate, is it effect modification? If it's not effect modification, is it confounder? You may find out that if it is effect modification, that is good. That shows that it's not a confounder. It may not be effect modification. You want to test if it is a confounder. It may not be a confounder. That shows that it's neither effect modification or not a confounder. So it can be effect modification without being a confounder. It can be a confounder without being effect modification. But it can also be that there is neither a confounder or effect modification. It's a step. So now, if the effect of exposure on disease vary according to the level of confounding variable, then we say that the variable modifies the effect of the exposure. That's what I've just said. If you split your analysis, if the effect differ on the two different strata, it's a modification, it's not a confounder. In a confounder, you expect the effect to be the same. Now, a number of different terms have been used for this effect modification. They call it effect modification. That is, the variable modified the effect of the exposure on the disease. They call it interaction. It's the same name. So when you see effect modification, interaction, heterogeneity is the same. So they call it interaction. There's interaction between effect of exposure and confounding variable. Or there is heterogeneity between strata. The estimate of the exposure to disease association differ between the strata. So I want you to, how do you test for the effect modification? Just like the way effect modification, confounder, you evaluate and remove. Effect modification, you cannot remove. You just test if it's there and explain it. So what people that are just logging, I will be removing them. Okoli, Eukarya. I don't know why people are just bringing to the Okori. Dr. Okori. Unmute yourself and talk. Dr. Okori. Dr. Eukarya.
Good evening, sir.
Good evening. How are you? So you didn't pay for the workshop. Workshop is workshop you pay for. You didn't pay. You just came in. You didn't pay.
Okay, I didn't know that I was supposed to pay. I'm sorry.
This one is a workshop. Is what will be. It's a weekend workshop from tomorrow, today, tomorrow, and next tomorrow. So if you want to, unless you want to stay and pay, otherwise it's for the people here. They pay for it.
I don't know how much is it.
It's 15K.
Okay.
So if you want to stay, you can stay and pay. Okay, let's just move further. Now, the use of regression model to examine effect modification or equivalent interaction is most flexible approach. The best way actually is to use regression. But when we use mental enhancing method, we will go to explain now, to control for confounding. An alternative is to use chi-square test for modification. Can you see now? So in trying to remove confounder, you also test if there's effect modification. I'll go to the next slide, talk about that 5 steps. Now, let me just keep this one. Let's just a practical approach to examining effect modification now. The practical approach, always examine the pattern of odds ratio in the different strata. How different do they look, and is there any trend across strata? So when you do your analysis strata by strata, you split it. For example, now this example we gave for the 2 age group, you do it separately. You look at you look for the odds ratio of the 2. If there's a clear evidence of effect modification and substantial difference in the exposure disease association between the strata, report this and report the exposure disease association separately. What it's telling you is that if you do it, you see that obesity and cardiovascular disease, the relationship, the odds ratio is different from the for obesity and cardiovascular disease. For the people that are less than 50 years, the odds ratio is different from the people that are more than 50 years. And they are significantly different. That shows that it is effect modification. You report it like that, like for so and so. For the people that are less than 50, they are more, the people that are obese are one time more likely, or 1.5 times more likely to have cardiovascular disease. For the people that are above 50, people that are obese, they are 10 times more likely to have cardiovascular disease. You report it like that. That is an effect modification. In that case, age is not a confounder. Because if the age is a confounder, when you have separated, the odds ratio will be the same. Because you have already removed the effect of age. If there's a moderate evidence of effect modification, use Martin-Hansen method in addition to report stratum specific estimate of the exposure disease association. So what is just telling you is that if there's evidence or moderate evidence, just like what you use Martin-Hansen method in addition to report. If let's say there's this, you know that as they are different, all you just need to do It will say effect modification, just report their odd ratio separately and go. But if you see that there is no, well, you are still, the difference is not much, you still go ahead and do further analysis, which we are going to discuss now. If there is no evidence of effect modification, report this and use Martin-Ensing method. This Martin-Ensing method, okay, let me just, the 5-step, because this 5-step I have here, just summarize it. I don't want to, because before I don't want to talk much until we go and just want to just talk less, so that when we run it, when you see it happening, the way it is, you can discuss further more. Look at this 5-step in doing stratified analysis. And this stratified analysis, we have already said something. You are looking for 2 things: effect modification and confounder. First, you test crude association, calculate odd ratio or relativity before stratification. First of all, do lump sum. For our example now, what is the odd ratio for the effect of obesity on cardiovascular disease? Just do it once. Once you do it, you have the crude value. Then conduct stratified analysis now. The first one is not stratified. You didn't split them into strata. But the second one, you now split them. Conduct stratified analysis. Calculate odd ratio or relativity for each level of confounding variable after stratification. Can you see the second step? So the third step, test homogeneity. You want to have a value. We have already said that if the value are the same, that shows that it's not effect modification. If the value of the odd ratio you get for the different strata are the same, that shows that it's more likely to be a confounding rather than effect modification. If they are different, that would be effect modification. But you know, it's not that it will be have to be the same. If one is 2.3, the other has to be 2.3. Something may be, no, they will be different non-value, but you put it to test to see if there is a different or not. That's what you mean by being the same. If you put it to test, though you are seeing different value, you see, it's not statistically significant. There's no difference. That shows that it's the same. But when you see the values are different and you put it to test, it shows that they are different. That shows that they are different. So being the same does not mean that it has to be the same figure you are looking for. You know, it will not be like that now. Most of the time, you cannot exactly get the same figure before you can say that they are the same. So now, after you are conducting, you now do homogeneity. So homogeneity means you want to test that these separate odd ratio are they the same? Homogeneity of odd ratio or relative list to determine whether this measure of association are significantly different. This can be done by conducting Breslow-Day test of homogeneity. You're going to see it, we run it. A significant test indicates a significant interaction or effect modification. That is, if there is a, you know, you are testing for homogeneity. The null hypothesis is that these different odd ratio for different strata, they are the same. If they are the same, that shows that it's homogeneous. That shows that there's no effect modification. But if it indicates significant difference, that shows that there is interaction or effect modification. In this case, then it is preferable to report separate odd ratio and relative weight for the strata. That is, if they are different, just report the separate. Then the next step, calculate Martin-Ensing odd ratio or relatively if the test of homogeneity is not significant. If let's say it was significant, you stop at number 3. If it's significant, that shows that it's an effect modification. It's not, that particular variable is not a confounder. But if it's not significant, it shows that they are the same. Then you now go further. Now calculate Martin-Ensing odd ratio or relatively to test homogeneity of the homogeneity if it's not significant. Now, conduct Cochrane Martin-Ensing chi-square test to evaluate significance of adjusted odd ratio. Don't worry, we just go straight into practical. We look at an example so that I don't, because when the talk is much, it can confuse. I don't know if you have any question before I move further. Let's now see the way we do the stratified analysis now. How we do it manually, then before we run it. How we do it manually before we run it. Any question before that time? Any question? Okay. No question. Let me move forward. Oh, people are not sleeping. Yes, let's look at. Yes.
Sorry,
Yes.
before you move on.
Okay.
When you are talking about the differences in odd ratio for each state from each atom, when you compare about 2 or 3 different levels, I read somewhere that there's a kind of percentage that you ascribe to it. I think maybe if it's more than 10% difference, that is when you think there's a significant difference or something.
Where that one is just talking into the air. I've seen it before, but it's not. Those are the crude way before, but there is that significant test. Yeah, there are significant. Go to see. We are going to run it. There are significant tests.
Okay.
There are significant tests here. They say that if the difference is certain percentage is effect modification. If it's not up to that, it's not effect modification. But the issue is that that is just a what do I call it? It's an arbitrary. Those are arbitrary value, but there are tests over the years. Some people, intelligent people, also develop some tests to test for it. That's what we call the homogeneity test. We are going to see it. We are going to try to calculate. Though the stratified analysis, the way you give weight to it, it's a little bit tricky. But since it's workshop, we still take us through it. But if you cannot grab everything there, you don't actually need to, because all you need to know is to know what to press and the step to and how to interpret the result. That's all. So because the mathematics of it also can be so tricky, but it's not something that is difficult to understand also. But in a situation, if you didn't understand everything about it, but once you understand what it means, how to interpret the result and how to press button to go and analyze it, it's enough. So let me quickly go into the way they put the weight. So how you do the stratified analysis? Let's say we want to do it with hand now. So unless it appears that the association between the exposure and outcome varies markedly between strata, we usually wish to combine the evidence from the separate strata and summarize the association controlling for confounding effect. No, look at the first statement. Unless it appears that the association between the exposure and outcome varies markedly between the strata. If it's very marked, you can see it. Physically, you know that this is effect modification. You know it's not a confounder. But when it has not really marked, you just see that they are different. But maybe you have even put the test. It's not. It shows that it's the same. There's no much difference there. So you cannot see. Okay, maybe you have 3 or 2 strata and the strata and the odd ratio they are very close. Will you be reporting the 2 odd ratio? You cannot. And that's why intelligent people say, what should we do? There's a way to combine the odd ratio or the odd ratio by having like a mean average odd ratio. And for you to have the average odd ratio, you must give weight. That's what I want to do here. You must give weight, because if you have different strata, the accuracy of the odd ratio you are calculating is not the same. The one that have more sample, more people in the stratum is more accurate. As we already talked about standard error before, when sample size is high, the standard error is smaller and the measurement is more accurate. No, when sample size is high, it is more accurate. So if you know that this different strata you have is defined by the third variable. So each stratum will not have equal number. All the strata will not have equal number of people subject in them. So if that is the case, you want to have the highest, we have more accurate odd ratio somehow. So in order to do that, you have to look for a way of giving weight to the odd ratio.
So you're breaking. I can't hear you.
Breaking? Can you hear now?
Yes, sir.
So you have to look for a way of giving weight to the odd ratio. So after calculating odd ratio for each of them, we want to combine the odd ratio to make one. We calculate average odd ratio. Then how do we calculate? You cannot just add all the odd ratio and divide by 4. If they are 4, I'll divide by 2. Because each of them, they don't carry the same weight. So in order to calculate this, so the intelligent one has, okay, the weighted average odd ratio now. That is, the average odd ratio we are looking for should be odd ratio that you sum up, you multiply the weight contributed by each odd ratio by the odd ratio, and sum everything and now divide by the total sum of the weight. This starting point, I don't know if people understand it. It's very simple. You have, let's say you have two odd ratio now. You want to calculate average. It's not just by saying you want to calculate weighted average odd ratio. Base that is weighted. If it's weighted, you cannot just add the two odd ratio and divide by 2. Because if you do that, you are telling us that both of them carry the same weight. Both of them, since they don't carry the same weight, how do you calculate? What you should do is that you have to multiply each odd ratio by the weight it has. So that the one that carry more weight will have bigger value. You now add all of them together. That is the weight. W here is the weight times the odd ratio. The weight multiplied by the particular odd ratio, you now add all of them together and divide by the total weight for all of them. So it will give you the average odd ratio. Does anybody have problem understanding that? Now.
So, sorry, sir. So just to confirm, the
Okay.
summation will be like, let's say there are 3 different odd ratios now. So what you're saying is that the summation of W times the first OR, that's the weight of that first OR times the weight of the
odd ratio,
that first OR
and you add
plus
it to the other one, yes.
the weight times, okay.
Exactly.
Then over
the total weight.
Then
you go and add all their total weight.
Over will be the weight of each of them. So the weight of the first one, weight of the second one.
Yeah, add it to exactly summation exactly.
Okay.
Does it make sense now? It's just the way, just playing on mathematics. So after you have done that, write the same one. Sir? So we are going there. Where you get the way, we are going there. We are going there. The thing is not moving. I don't know why it's not. I want to, yeah. So Dr. Abasi say, how do we get the weight? So that's where we are going. So let's look at, if let's say this is a 2 example now, 2 by 2 table. So you know this, well, the odd ratio, the formula for odd ratio, AG over BC, you will need to be explaining how you get to it. And this is the, though most time in nothing as the method talk about odd ratio, but it can be extended to relative risk also. That's why I also put the relative risk there. But most of the time, what you measure is the odd ratio. But the same process. Imagine if it is a core study you are doing, you want to talk about relative risk. So that's why I put it there. So this formula for odd ratio, if you have been following us, does anybody have any problem? If you don't have problem, if you have problem understanding it, I will explain it. The way why it is AG all over BC. And this is for formula for relative risk. A all over A plus B, everything all over C plus all over Z. Please, if you have issue understand, let me know. I will explain it. Otherwise, we'll just move forward. Because there are some. Yeah, what do you say?
I think I have visual about it, sir.
Okay. Okay, no problem. Okay, no problem. I like using live. Something is making noise. It's Dr. Ogunde, please. Once you finish talking, if your end is making, just mute. Yes. Yes. Yeah. Yes. Now, okay, let's just look at this example here. Dr. Ogunde, so you are following. Look at the example here. Now, let's take this first one. Obesity, cardiovascular disease. I just want to demonstrate how you calculate, how you get odd ratio, that formula that is odd ratio. I cannot write there. I thought I should be able to write on this thing. Okay. I thought I should be able to write. Okay. Okay. Now, as for example, if you have something like this, you know, we say this is A, B, C, D. Of course, this one will be A plus B. This is C plus D. That's the total here. This one is A plus C. This is B plus C. B plus D. This one is, let's just say N, because that's total A plus B plus C. N is sample. This one just telling you the exposure and outcome. This is disease positive, disease there, disease negative, no disease, exposed, non-exposed. Now, if you look at the example we have there, if let me just put some arbitrary value. If let is the same thing now, you now have the same this table. Sometimes it's not, when you are rushing too much also, people will lose, will not gain much. So the same table now. So let's say we have something like this exposed, non-exposed, disease, no disease. Okay, let me just quickly check what we have in that our this thing. 10, 19, 35, 465. Okay. So this is 10, 19, 35, 465. So this one is 100 here, total here. This one is what? This is 500. So total is 600. And this is 45. Five, 5. Now, if you remember what we say, we want to calculate odd ratio. Odd ratio means you are trying to look at dividing, comparing two odds. Yes, I mean now. So let's assume it's a case control study. Since we are talking of odd ratio, we are starting with people that have out of 45 people have disease here. 555 did not have disease out of 600 people. So if you want to calculate odd ratio, I want to say, okay, out of these 45 that have the disease, what is the odds of exposure to maybe obesity, of obese, odds of exposure? So you remember, you know that here the people that are obese 100, total that are obese 100, people that are not obese 500. Are we together now? So if you look at it, among these 45 people, 10 are obese. If you look at it from there, so you see, among these 45 people, these people that they have the disease, No, if let's say you want to calculate, okay, let me it's easier for relative risk first. This is people that are exposed 100, 500 are not exposed. 45 have the disease, 555 is not. If you say what is the relative risk? Relative risk means risk among the exposed over risk among the not exposed. So who are the exposed? The exposed are 100 people. How many people have the disease among the 100? Is 10 over 100. That is the risk among the exposed. 10 over 100. That is the risk among the exposed. Among the non-exposed, what is the risk? 500 are not exposed and 35 have this. So everything over 35 over 500. You will see now, this formula is the formula I wanted to bring out. This A is the 10. A plus B is the 100. Are you following? So that is why that formula is A divided by A plus B. That is 10 all over 100. Everything all over 35 here is the C. Can you see? I will remove you. If you make noise again, I will remove you completely. General Fiona. So,
you.
Welcome.
I'm fine.
Yeah, well, yeah.
Thanks.
Okay, thank you. So, C over 500 means C plus D. Can you see? So, the formula is a relative risk you are seeing there, A into A plus B over C into C plus D. That is the formula for relative risk you are seeing. Now, odd ratio is a little bit, to explain it, I will explain it because I want you to get the logic. You know the odd ratio, odd, we have already said odd. What is odd? Odd is probability over 1 minus probability. Of something is the probability of that thing over 1 minus probability of that thing. And that is 1 minus probability of that thing is the probability of not having that thing. That is a complement. So now, if you want to calculate odd ratio, among these people that is somebody asks a question or is making noise. So among these people that have the disease now, 450, 10, we have 10 here. Now, these 10 people are the people that smoke. These, you know, that smoke, yes. These 35 are the people that did not smoke. Among them, 10 spoke, 35 did not smoke. So if you want to say, if you want to talk about odd now, odd or smoking or not smoking, if you want to start with probability of smoking, all you need to say, okay, among these people that are exposed, among these people that have this disease, what is the odd of smoking? The odd of, so what is the odd of smoking? You can calculate for the probability. It means that the probability of smoking, which is 10 over 45 over probability of not smoking, which is 35 over 45. Can you see? Now, you know, if you remember in mathematics, this type of thing, it becomes 10 over 45 times, want to change this division to times now, it becomes times 45 over 35. So 35, 45 cos 35, it will mean 10 over 35. It's just like saying 10 over 35. Can you see now? That would be the odd or smoking among the people that have the disease. If you want to know for the people that don't have the disease, odd or smoking, if you do the same long way, it will end up with 90 over 465. If you say 90 over 555 divided by 465 over 555, when you change it 555, we still cancel 555, it will become 90 over 45. So the odd ratio now will be odd ratio. The ratio of this, you want to divide the odd or smoking among the people that have the disease over the odd or smoking people that don't have the disease. It will now give you, that is, you are saying 10 all over 35 divided by, you are dividing by 90 over 465. 465. If you change the subject also, it becomes 10 over 35 times 465 over 90. Now, what I want you to look at, now, look at who is making noise. Look at. So, General, if somebody is making noise from your hand, please note. Now, look at it. Look at this. What is 10 here? 10 here is A. What is this 465? Is D. Can you see? D. What is 35 there? 35 is C. And what is 90 is B. And that is why you see odd ratio is AD. That is, you just call this and this over this and the over BC. That is 10 times this 40, can you say AD, 10 times 465 times BC, 19 times 35. That is where the origin of that formula odd ratio is the constant. Look at this formula also. Before I change to that slide, I want you to see this formula for relative rate. You see A into bracket A plus B over the. You can change. You can still change for subject. A, it will be A into, it's like you are saying A into C, A plus B rather, times, if you change this thing and change division, change to times, what will happen? It becomes times C plus D over C. Can you see? Because you know your A into A plus B divided by C into D. So if you change this division into time, this C plus D will come up because C plus D over C. So it's the same thing as saying A into times now. It's not division. C plus D over C into A plus B. It's just on mathematics, you just play with here. So if I go back to that, because what I was, look at here, this is where we are. So can you see the odd ratio now? AD all over BC. I think it's clear the way you will get it now. So the relative risk is A into this, which is what I just changed now to become A. So this and this is actually the same. Just to try this one, this, why this is not right? And this is called is the same. So let's move to the next slide. No, sometimes when you just put formula, people just find it difficult to understand. But if you break it down with a normal life example, you easily conceptualize it. Now, this slide. So the relative, if you want to put weight now, Martin-Hansen estimate of the summary odd ratio and relative risk denotes this, and the weighted average, because that's the question Dr. Abasi was asking. How do you get the weight? So, you know, the total, grand total is n. So the weight will be from the denominator provided by each of them. For the weight for the odd ratio will be the denominator of, if you remember, the odd ratio is A over B plus C, BC. So because n is the total. So the weight of each odd ratio will be determined by the denominator of each odd ratio. So that is why they now put the weight for each one will be denominator, what the denominator contribute to the total. Can you see? So that is why the weight for odd ratio for each stratum will be the BC for the stratum all over n. For if it is relative risk, it's going to be, you know, this is the denominator for the relative risk. It will be denominator of this stratum of the relative to the. So, you know, if you look at it now, we are pari passu, we are trying to give out the formula for to consider both the odd ratio and relative risk at the same time. So now, if you now come here, no, we have already said this one is just one funny mathematics. If it's not taking, people may even be, but it's not so difficult. From what we have just seen now, you can easily write this is equal to A. You know, this is the weight now. WOR will be equal to that, the weight, A, B, C all over N. No, sorry, this is the, you can easily write the formula for the this thing and replace, you know, the odd ratio, the denominator is BC, and that BC is 4. So if you change the formula, you can change this one now. Sorry, I don't know why this thing will not write directly. Let me see. Okay. Okay, maybe let me go to that. I want to do something. Yes. Yes, this weight, let's work on it. Let me just trying to erase. Now, you know, we say that the weight is equal to BC all over N. If you change the subject, you try, you can say that, you know, this one means all over 1 also. So you can say BC is equal to WN. So if you say BC is equal to WN, N, of course, will be also be BC all over W. But just look at BC WN, and that is what is used to replace if BC is WN. So the weight, let me go to that. If BC is equal to WN, which is weight all over N times N. So W, can you see now? So that N now, you use to replace the BC here. So in that case, so instead of writing BC now, Can you see? You can now, this weight is here, so it comes here like this. So when you now look at that formula we have written before, that this is the Martin-Hudson odd ratio weight times this, you can now write for this numerator now will be this A plus, can you see, weight times odd ratio. You put it here, and this is the weight which we have gotten before as BC all over N is here. It's just some mathematical manipulation to calculate it. And it's the same thing you do for relative risk. You may not bother yourself much. So look at the example now. We have broken that thing into the two strata now. This is the overall. This is strata 1, age less than 50, age 50 and more. And when you come to put in the formula we just put now, it will calculate the. Look at the odd ratio, the crude odd ratio. We calculate odd ratio for each of them using the formula for odd ratio for age less than 50, for age greater than 50, overall, which is the crude. Relative risk for age less than 15, greater than 15, this overall. So what this overall are the crude odd ratio, crude relative risk. These are the odd ratio for the each stratum. Look at for this one, odd ratio 1.48, 1.54. And look at the crude odd ratio 1.93. Can you see both of them? When you do the crude, is 1.93. When you stratify, it slash the odd ratio down. And each of them, you look close, 1.4, but they are different, but they look close. But we cannot actually say if they are different until we put it to test. If we put it to test, but it will look as if they are not actually different. And they don't look too much. If they are, you put it to test, they are not different. That shows that is likely to be a confounder. But if they are different, that shows that it's effect modification. Look at the relative risk 1.43, 1.44, and the crude oil relative 1.79. So when we now do combine these two ND, we are trying to what this is to calculate the average odd ratio for these two. Combine them. When you combine them now, what is give you 1.52, or you expect it to be a value in between the two. The same thing. This is 1.44, though it's holding the value of this one, but maybe approximation is maybe this one should be bigger, small, but maybe approximation is this, see the same thing. Can you see now? This is the Martin-Hudson odd ratio. This is relative risk. I don't know if there's any question. We want to run it now because we have the data set. We are running so that we can explain further. Any question concerning what I've just discussed? And if the mathematics is looking so difficult, we just leave that. Just know that we have calculated odd ratio for each of the stratum using the formula for odd ratio and relative risk. Any question? Any question? No question. Okay, let somebody share the data set I share with us, obesity and CVD. Who will share? We should not find difficult looking for somebody sharing. Obesity and CVD. Nobody? Dr. Fatima. Jane, have you opened your own?
Okay, I'm using my phone.
Okay, you are using phone. Who will share? Ugo, you can share your own. Dr. Fatima and Dr. Bako. Yes, okay. Anybody that you can quickly share. Because I don't want to do the talking and also do the sharing. There should be division of labor. So because I have it here, so but so who is sharing now? Most of you have not even downloaded it. So
can I share it, sir?
Yeah, you can do that. You can do that. Okay, let me allow you to share.
Okay.
So you can share now, Dr. Fatima. That's great. Yes. Great, we can see. Now, let me just explain. You will see that there are actually three variables there. This cardiovascular disease, yes or no, is the outcome. The obesity, obese, yes or no, is the exposure of interest, is the factor. The age, less than 15 and greater than 15 or more, is a confounder you want to look at. So it's a factor also, which is so both age and obesity are factor to cardiovascular disease. We have studied obesity now. So we want to see age is a confounder or effect modifier. Now, this serial number is just a serial number just to put there. It's not necessary, but just there. But if you look at the other one, I put age, logistic, it's me that created that for tomorrow. Then we talk about logistic regression, because the way you run it, you have to create dummy. I just created that dummy there. So that one, all this one I put logistic, the same thing as the age group, as the obesity and the cardiovascular, but I created those ones for logistic regression. Now, what we want to use now is that let's first of all do the crude odds ratio. Let's just do the cost tabulation first before we do the stratified analysis. So go to analyze, Dr. Fatima, analyze. Go to analyze. Are you there? Dr. Fatima? You may have to unmute yourself so that I can hear you. Are you there? Go to analyze. Isn't that people are not hearing me?
We can hear you.
We can hear you.
Yeah,
It depends on who shared it. I thought it was Iguilo that shared this.
No, it's Dr. Fatima that shared. It's like our network is bad. She's not hearing us.
Sorry, sir. I was not sending apologies because I was like, because this is a new batch, I didn't want to, because I shared last week. I didn't want to get
Forget about that one. That is you that is bringing that apology.
I can share, sir.
Okay. Yeah, you can share, but I don't know if you can share upon it. Try and share now. I don't know if he's hearing us because it's a network.
Fatima's one is still there now.
No, the network is not hearing me. So the network is full of Twitter, I think. It's the network. Okay, Dr. Prof, try and share. No, you cannot share.
Fatima is no longer on the list of participants. I'm sure she's.
No, I'm seeing her now. It's here, but.
Sorry, sir, it was the network.
Yeah, it was network. Okay. I was saying that you should go to analyze. So is your network back now? The prof is already sharing. Okay. Then go to analyze now. So go to descriptive statistics, then cross tab. You know it's about contingency table. Anything about contingency table is cross tab. Yeah. Now the row will be obese. Obese is the exposure. Then the outcome is CVD. Yeah. Let's go to statistics. So no, you don't need the chi-square. Risk, yes, that's all. Let's just stop there. Risk. Okay, it's okay. Yes, we are already seeing the result. That's good. Just yeah. So we can see that the odds ratio is 1.93, and that was what we got also. If you remember the slide I showed, is 1.93. The odds ratio is now 1.93. Then the relative risk is 1.79, if you remember. It's the same thing you are seeing. And if you look at it, if you remember what we discussed when we were discussing in confidence interval of odds ratio, you can see both of them are significant because it does not include one. Yes. The relative risk and the odds ratio are significant. And you see, the odds ratio 1.93, the low confidence interval 1.28 to 2.91. So you see, so that is the crude odd ratio now. So let's go and do the stratified one now, sir. Analyze.
Sir, please, I didn't understand that part.
Okay, wait, sir. Which part?
You said
Your network also, your DC. I cannot hear you.
hello, sir.
I can hear you now. Go on.
Yes, you're saying that it is significant, and I don't know if you got.
Okay. That's that you have not been part of our
Class. Like
Yes.
series.
You were not in a series. Yes, I will explain it now. No problem. Let me explain. Yeah. Let me see if I can. Okay. Prof, just stop sharing so that I'm trying to. Thank you. Let me just quickly explain. What were we? Where's measure of association? If you remember what we presented on yes. What we presented on Thursday, is it Thursday or not Thursday? Is yes, we presented on Tuesday. We talk about interpreting odd ratio. You know the odd ratio you are looking at, or relative risk. You are trying to see the risk of this the disease among the exposed group divided by the risk among the non-exposed group. So that's why they call it ratio. Ratio is gotten by division. When you say you have calculated a ratio, it means that you have divided one thing with another thing. And because the two things you divide, they are similar. They have the same type of quantity, so the unit cancel out. I actually give an example. If somebody travel 400 kilometers and over 4 hours, if you divide 400 kilometers per hour for the 4 hours, it gives you 100 kilometers per hour. That is the speed. It's not a ratio because it has the unit 400. The numerator is in kilometer. The denominator is in hour. So it will give you 400 over 4 will be 100 kilometers per hour. Then if you say somebody travel 400 kilometers, another person travel 4 kilometers, you now divide 400 kilometers, you are comparing the two. You divide 400 kilometers by 4 kilometers. It will give you 100, but now it's not 100 kilometers, it's just 100. It's a ratio because both the numerator and denominator, they are distant, they are the same unit. That is clear. So ratio has no unit. So what we do in odd ratio or relative risk, you measure the risk of disease among the people that are exposed and measure the risk among the people that are not exposed. Both of them are the risk. So because you are envisaging that exposure should be able to cause is the one causing the disease. So because of that, you now you are comparing the two risks. So how do you compare? You now do ratio, you divide them. You put the one that are among the exposed as the numerator and the one that are among the not exposed as the denominator. Of course, if both of them are the same, if the risk of the disease are the same among the exposed and among the not exposed, if you divide them, it will give you 1. If you say 35 over 35 is 1, 60 over 60 is 1, 5 million over 5 million is 1. Anything, both numerator and denominator are the same, it will give you 1. So in that sense, if the disease, the risk of the disease is the same among the exposure, which you move exposed group, which you use as the numerator, and it's the same with the risk among the not exposed, which you use as the denominator, it will be 1 when you divide it. It means that the disease, the exposure yes, because that is the risk is the same. Either you are exposed or not, it's the same. So it's not the exposure that causes, it's something else that is causing the disease. It's not that factor you are talking of. That is why the disease is either you are exposed or not, the disease is the same. It's not that factor that's causing it. But if the disease is higher among the ones that are exposed, you make the numerator, it will be greater than 1. So because if the numerator is bigger, it will be greater than 1. It will now give you, okay, that shows that exposure is the one causing, because the risk is higher among them. When you divide by the other one, it's greater than 1. So when the risk is higher than 1, when the odd ratio relatively is greater than 1, it shows that that factor is responsible. It can be in the other way, that the numerator is smaller than the denominator. That shows that the numerator, which is the risk among the exposed, is smaller than the risk among the non-exposed. When you divide it, it will be 0 point something. When it is 0, it means that that shows that even the people that are exposed, they are less likely to have the disease. The people that are not exposed, they are more likely. That shows that that exposure is a preventive measure. So when the odd ratio is less than 1, that shows that that particular factor you are looking at is preventing it. It is when it is greater than 1 that you can say the factor is causing it. If it is 1, the factor has nothing to do with it. Now, you can see that to really know whether it's significant or not, that is the cause of the question, whether it's significant or not. We have explained it many times. Now, what is the confidence interval? Confidence interval is another inferential method separate from hypothesis testing. It is hypothesis testing that gives you p-value. Think of anything you test, either t-test, chi-square, ANOVA, you end up with p-value. It's hypothesis testing. But the confidence interval is another inferential method, different from hypothesis testing. And it gives more information than the hypothesis test, than p-value. Now, how does it come? What you do is that what, like the relative risk you calculated or odd ratio, is you calculate is one value. We call it point estimate. Is for the sample you took. Is it not from the sample you calculate it? That is statistic. Statistic is what you get by summarizing your sample. But the real relative risk in the population is a parameter. We would have gotten that if you can study the whole population. Since you cannot study the whole population, you take sample. Whatever you get is statistic. But the real issue is in the population. Now, whatever you get for your sample is an estimate of the population parameter. Now, you cannot be sure, since you did not study the whole population, the parameter, you cannot be sure that your statistic is equal to what the parameter will have been. Now, what you can now do is to now calculate a range of value around that estimate. That estimate is, who is that? I thought I was sharing this. So I thought I was sharing it. I wasn't sharing it.
No,
Bro,
sir, you weren't.
You weren't, sorry. I thought I was sharing. I went to open, no, not this one. Okay. But the person is getting I was showing I was sick. Well, some of the things I talk here is, let me just quickly conclude that. Yes. So I'm sharing, you can see it now, right? What I was talking at. So now the confidence interval now, what it does is to calculate after you have gotten your, let's say, odd ratio now. You want to be 95% sure that in the population, even though this is what I've got in my sample, I'm 95% sure that in the population, the value will be between this and this, 2 intervals. Those 2 intervals, you somehow you calculate it from what you have gotten by calculating standard error. When you now combine it, is somewhere it's just some mathematical manipulation, which you don't need to bother yourself about it, because if you press computer, it give it to you. They just know that He just use the standard error together with what you have gotten. He will now give you a value that is less than what you have gotten and give you another value that is more than what you are getting. So what you have gotten is in between. So that range of value now, the lower value and upper value, you are 95% sure that in the population, the value will be in between. That's confidence interval. Now, the interpretation of the confidence interval for ratio, when you say ratio, odd ratio, or relatively they are the ratio, is different from when you are looking for interpretation for difference between mean and proportion. But we are talking of ratios now. Now, if you actually draw something also so that, okay, you don't even need to draw because the thing is here. Look at, if 1, we have already said that 1, whenever there is no association, if the numerator and denominator is the same, if the relative ratio or ratio is 1, it means there is no association. That exposure has nothing to do with the disease. Now, if you calculate your confidence interval now, 4 things can happen. And these 4 things, what is depicted in this slide, on this slide, the 4 things that can happen. 1, this value you have here, you see the confidence interval, you see the lower, upper, then the middle is the value you have calculated. So in this one now, you will see that both the lower, the calculated value, and the upper value, they are less than 1. What it's telling you is that the range of value in the population is in between this and this. Now, look at this second one. The lower value is less than 1. The value calculated is less than 1, but the upper value is greater than 1. So what it's telling you is that even though I calculated something less than 1, but the range of value in the population will be between this is 0 point something, which is less than 1, over to something greater than 1. So it can be anything. 1 is one of them. So you already know. If you know that if it is 1, there's no association. So if the range of value include 1 in the range, it means that it could have been 1. So in the population can be any value from here to here, including 1. That is why it's not significant. So this first one is significant. The only difference is that everything is 0 point something. Even the lower value is 0 point something. It's not 1. The real value you calculate is 0 point something, is not 1. The upper value is 0 point something, is not 1. What it's just telling you is that what you have calculated, the relative rate or odd ratio is 0 point something. It means that it's less than 1 and it's significant because the range of value has not crossed 1. The only thing there is that that shows that that factor is protective because the numerator will have been smaller than the denominator. That's why the thing is less than 1. And the numerator is the one which is for the exposure. And the exposure to the factor. The denominator is the one that are not exposed. That shows that that particular exposure, if you are exposed, you are less likely to have the disease. So it's protective. But when you come to this third one, what you calculated is greater than 1. But the lower value is less than 1, the upper value is lower. So the confidence interval has crossed 1. It can be any value, including 1. That shows it's not significant. So this last one is significant because the range of value does not include 1. And everything is greater than 1. It means that whatever you get, that shows that that factor is causing the disease because the odd ratio is greater than 1. So you will see 4 scenarios here now. 2 are significant, 2 are not significant. Those are the things that can happen. Those are the 4 scenarios that can happen. So if significant on the opposite, on the positive side, or the greater than 1 side, it's telling you that that factor is causing the disease. If it's significant on the less than 1 side, it's telling you that that factor is protective. So if it's not going to be significant, either you calculate something less than 1 or greater than 1. The confidence interval will start from less than 1 and cross 1 to anything greater than 1. It will not be significant. So this one we just calculated now, you can see it's from plot is anything greater than 1. So, Prof, you can share now. Let me stop sharing. You can share. So, is that clear now? The person that has the question, is that clear?
Yes, sir. Thank
To
you.
everybody. Okay. So, what you do is what you do is that all our what do I call it? Our videos, they are on it. Just subscribe for you. Some of you have discussed them extensively. You get to get all those all those small things. Just after yourself, or even the video for this was all we uploaded there. So you just subscribe. It's just a token of subscription. You have access to everything there. And at your own leisure time, you can watch. Yes,
All right,
I just do that because if you come for a lecture, I don't want a situation where from day one you are blank. So you must explain some fundamental things. But all those things we have explained them over and over. Okay, Prof, share. So let's look at the result. Thank you, sir. You can see now that the crude oil ratio 1.93 and the confidence interval 1.28 to 2.9291 rather is significant because the confidence interval has not crossed 1. So, Dr. Wale, you can see the reason it has not crossed 1. The reason is significant. It has not crossed 1. It doesn't include 1 in its range. Now, let's do the stratified one. Let's analyze. Yes, now click on the statistics. You will see down, you see Kroken and Mantel Hansen. Click continue, sir. Then you need to move that age, move it to this layer, age group, yes. Move it to this layer. Can you see now? Because we are stratified by that factor, that's the factor we are using to stratify. Let's click, okay, sir. Can you see? Okay, wait, let's start looking at it from the beginning. You can see, okay, scroll down, the fair confidence table on CVD age group. Yeah, this was okay, sir. Wait, sir. You will see that this is the total, the one we have done before. The total class is down here. Total. The one for less than 50, the one for greater than 50, can you did it separately? Scroll down, sir. Let's look at the estimated risk. You can see the odd ratio 1.48, the one we calculated. It's okay, sir. Can you see 1.48 for the first group, the second group 1.54. That's what we calculated, and both of them are not say. Okay, let me ask. It's workshop. Dr. Wale. Dr. Wale. Yes. Look at this one. Look at the confidence interval. Is it significant? Look at this first one. The odd ratio is 1.476. And look at the confidence interval is 0.7 to 3.088. Is it significant or not?
It is not.
Yes, why?
Because between 0.7 and 3.08, 1 will definitely come.
Thank you. Yes, so it's not significant now. So even the second one also is not significant, 0.8.
Not significant.
Yeah. But it's only the total one. No, we have done it before. It's just repeating the odd ratio for the total is 1.93. And look at the confidence interval is significant because 1 point something to 2 point something. So you can see that you will see that the odd ratio for each stratum is smaller than the crude odd ratio. And they are different value, but we cannot know how different they are until we look at the test. So let's scroll down, sir. The next table is the test of the homogeneity. It's okay. Look at the homogeneity test. We try to see, are they different? What do we see? Is there any different? This Breslow-Day test. So I want us to respond, please.
No, it's not.
Yeah, it's not. Yes. Somebody is talking. It's not, because if you look at it, look at the p-value, 0.932. So it shows that it's homogeneous. What it's telling you is that that's 1.45 and 48 and 1.54 is the same. No, the value are close, it's the same. So what does it tell us about effect modification now? Is there effect modification?
No effect modification.
Yes, no. Why did you say that?
Because there is no significant difference between the odds ratios of the two groups, of the two strata.
Thank you, sir. There's no effect modification, because if there is effect modification, the odds ratio will be different statistically, and that breast load day would be significant. So we now want to see, is it due to, what do I call it? Is it due to confounder now? So look at the next step. Test of condition. Yes, confounder. Can you see confounder? So look at it. Is there any difference?
Which one of them is that the test of conditional independence?
If they are the same, yes, yes. If they are the same, look, are they the same? Is there any difference? This one, we know what this one is looking at. Is comparing the crude odd ratio we get, and the maintenance odd ratio and the crude odd ratio. We want to see that is there any difference between them.
It's a trend.
There's a difference. This is a test for conditional independence, and it's not significant.
Which box are we using now?
So won't that mean that it is
conditional?
Look at the test of conditional. Scroll up, sir.
So if it is not significant, then it is not independent.
What is it? So if you try to see the crude and these Martinez, are they the same? Is there any difference between them?
The crude, where is the crude, sir?
Okay, let's scroll down. So look at the crude. We have already calculated the crude to be 1.93. This is the maintenance 1.52. If you remember in the calculation I did before, is 1.52.
No, this.
Yes, 1.52. Yes, 1.52. And you see the confidence interval also. If you look at it, you can see the confidence interval is not significant. Can you see? Are we interpreting? Are you following? Look at the confidence interval.
Please help us use the
what is not significant. And if you look at the chi-squares here, it's not significant. Are we together? So he's telling you that though it's borderline, if it's not significant, he's telling you that this thing is not a confounder also. But they already said that this test is not the power is not so strong. If you look at it, it's almost significant. But he's trying to say that this is not a confounder, it's not effect modification. But if you have to analyze it critically, the age here is not effect modification, it's more like a confounder. Because if you look at it, if we have to do all those logistics now, any p-value is 0.0, we still go ahead. Because what is the difference between 0.06 and 0.05? There's no much difference.
0.0.
What is the difference between 0.06 and 0.05? It's not much different now. So I will still analyze this one as a confounder. Any comment?
Okay.
Any comment?
So yes, I have a question.
Okay.
So
good.
like when we look at this test for conditional independence, that box, it means that when it is not significant, I wanted to understand the explanation for it. When it's not significant, what does it mean?
If it's not significant, it's telling you that the crude, we get the crude 1.93, and the one we now did the Mantenhensen. Mantenhensen, there's no difference. It's saying there's no difference between the crude and Mantenhensen odd ratio. This Mantenhensen odd ratio is 1.5. But if you look at it, it's almost significant, right?
Okay.
Do you get it now? So he's trying to say that this thing, the age is neither effect modification nor confounder. That's what he's telling us. But if let's say signal, you can be sure that we already know that the age is not effect modifier. They want to see if it is a confounder here. But it's at borderline. To me, I would consider it as confounder. Yes, I would consider it as confounder. Does it make sense?
Yeah.
Any question before I move forward?
Stop.
Okay. You can stop sharing. You can stop sharing. Yes. Before we close, let me just show some things. Yes. If you look at all those things we calculated, can use 1.52. That is the crude we got. So it's the same. Look at it, 1.52. That's the Mantenhensen we calculated. That's what we run also. So look at the crude odd ratio. Look at the one for the two group, this and this. Now, what I just want to show is that sometimes you can have more than. I just want to, because tomorrow now we'll be talking of logistic regression. I want to give you reason that nobody do this stratified analysis again, because the same work can be done with what do I call it? With logistic with regression.
Regression.
Yes, you will see if you have more than one. You can have more than. Can you imagine? This age now can be split to 5. If we have to do so, that we have to be battling with many 1, 2, 3 odd ratio. Try to summarize them to see. Now that's another one. You can have 2. If you remember when we were running it, where I say prof, you see layers. You can have obesity, family history. Maybe you want to, apart from obesity, is there a family history of the disease? You can have 2. You are looking at 2 effects of confounder at the same time. What it will do is that if obesity, if family history and male and female, you see, and the sex. If the family is 2 possible outcome, positive, negative history, male and female, it will give you 4, male and female. It will give you 4 stratum. And you see, with age, you can divide them into 5 strata. With this combine, you can divide them into, look at another example. You can even divide, let's say you combine both gender, age, male, sex. You can end up having even up to many strata. How will you be interpreted? So it makes it messy. And that is why the logistic regression has taken over. So you're going to see, by doing multiple regression, it takes over all those things. You can control for all those many confounders at the same time. Just like the way the linear regression replaces ANOVA, the same thing, logistic regression replaces stratified analysis. I don't know if you have question on this, so that we close for today. Any question on what we are doing? It's just for you to see the way we do do stratified analysis and try to see, is it due to effect modification or due to confounder? But the issue there is that even if it is effect modification, you don't remove effect modification. It's effect of confounder you remove. You just explain effect modification and say, oh, the effect of obesity on cardiovascular disease vary along the age. No, it's more marked when somebody is older or not. If, let's say, age was an effect modifier, that is how you interpret it. You remember, sir, Prof, when we did ANOVA, we also encountered such thing. When we were trying to look at, we did factorial ANOVA, bear goggle effect. when we look at people choosing mate, and they took pint of alcohol, no pint, 2 pint, 4 pint, and male and female. We now saw there was interaction between sex and the pint. And we discovered that when female they take alcohol, it affects them more in their judgment than when female take too. So there was interaction effect of sex. And that interaction is the same thing as effect modification. You know, you were asking that time, is it is a confounder? It's not a confounder, it's interaction effect. So the effect of the alcohol vary with the sex. Any comment or any question? I don't know why people are silent. Why are you silent?
Somewhere here. Sorry.
Is there any question?
Can you hear me?
I can hear you, sir.
Can you hear me?
Yes, sir.
Okay, can you hear me? Okay. You said that logistics with linear regression are taken over and over. Does it mean that in a study, it's not, which language do I use? It's not necessary to do ANOVA and go ahead to do logistic, this thing, linear regression in one study? Because there are some studies that I see ANOVA and linear regression together.
I'm not saying that. Some people can do that. You know, the reason is that though looking at many factors, the person may do, when you're having 3 groups, you may do, you use ANOVA, and somehow, in that case, the outcome is continuous. And apart from that, you may have many factors you even do the ANOVA for the examiner, and you have many factors coming in. When you have many factors coming in, you have to end up doing regression. But to be sincere with you, at the end of the day, well, you can still do your ANOVA, but when you went to summarize, you can still do multiple regression. But sometimes it's not necessary to do that ANOVA. Just do multiple regression. Okay. Examiner, especially if you do your ANOVA, you find you won't be doing post hoc instead of you doing post hoc. You know, you want to know where the thing lies. You do post hoc. You do or doing parent contrast. Instead of doing that, you just go and run your regression.
Okay.
Okay. Any other one?
Something that I wanted to clarify, sir.
Okay, sir.
That confidence interval.
Yes, sir.
I saw that the borderline you gave today is 1, that the thing crossed 1.
Yes.
But I thought it was 0. Because the confidence interval can be 0.08, it's less than 1. I mean, it's not up to 0 and forwards. I thought you used 0 in the other teaching. Sorry, I don't know whether you can hear me.
I think even Dr.
I understand technology, but I thought it was 0 when it crosses 0, because 0 now, if the confidence interval crosses 0, then
that's
that
interval
is null and void.
That's way different.
I think Dr. Ekobo can even answer that one, sir. Maybe Dr. Ekobo could answer. Let's see.
Is it 1 or 0? That's what I'm asking.
It's 1 here.
Mixing up the mean difference.
Okay, Prof, want to
It's mixing up mean difference.
Yes.
Yes.
No, I mean,
it's mixing up mean difference.
No, I mean the range of the
confidence
interval. Is it the crossing of 1 or the crossing of 0 point?
Okay, let me explain, sir. Let me explain. Okay. I thought some people wanted to explain this. You want to explain?
Let them explain. Let me hear.
Okay, Ugo, you wanted to talk.
Okay, no, I was just trying to explain that. Yes, I was just trying to explain that with proportion. That is when you're not using numerical now. So with proportion, like you explained, with the ratio. Once is the, for example, the exposure over the non-exposure. If one is if the exposure, like if there is no difference between the exposure and the non-exposure, because it's proportion, we will know that if, for example, the exposure is 3 and the non-exposure is 3, 3 divided by 3 will give us 1. But when we're looking at numerical values, you know, we what we use instead is mean. So we use numbers, and what we're looking at is different. So if, for example,
yes,
there were
Thank you, I remember.
Okay.
Thank you.
The explanation, but you need to, I am not so satisfied with that explanation. No,
I've gotten what she's saying.
Okay, wait, let me explain it very well. What he was trying to say is that what you need to say is not a matter, because there's confidence of proportion also, and it's the same thing like the mean.
Yes.
Okay.
This one is a ratio. Ratio means division. Here you are comparing by dividing. You are dividing the risk among the other group. So you are dividing 2 risks. So if both of them are the same, it will be 1. If the risks are the same, it will be 1. But if you are looking for difference between me, if you are looking at different, you are minusing. If both of them are the same, when you minus 1 from it will be 0. Can you see?
Yes,
so
sir, yes,
whenever you are looking at confidence interval of the mean or proportion, is 0 is the, because the 0 mean there's no difference for that one.
Is the mean.
It must not cross 0. The here, what
0
mean there's no difference in ratio is 1, because it's division.
It's 1, yes, sir. Yes.
So Ugo, can you say the way I explain it now? That's the best way to explain it, yes.
But I understood it from what you. Thank you so much. Thank you.
Okay, welcome. Because this issue, Dr. Ikobore raised it when we were doing, was it not on Thursday? Or is it Thursday or okay, on Tuesday? Because it says that some of our students, some of his students are there going for exam, and they raise it. How do you interpret the one for the mean? I said that they should go and watch.
Yes.
So, and it's because of you I gave you that deal. It's because it's in honor of your request. Because
I know.
Yes, because they are not, because they only come.
And you went to town and explained it very well.
So what they don't understand is that even they say you can subscribe to that thing and be watching it when you are less busy, even with your phone. Even if you are going something you are not busy, you can watch. And the more you get to know some of the rudimentary things, some of the things that we ask them in exam, they are just simple things, fundamental issues which they don't know.
This one is a proportion.
Yeah. So I think we can stop here. We can stop here.
The ratio.
So let me just pause any other question? So I will upload the video there, and anyway, maybe I should still try and send, because I have issue when I send it to mail. Many people, they have issue opening. Fatima, Dr. Fatima. Hello? It's on there. Hey, yes. It's like you never had issue opening when I sent the workshop video the last time. You didn't have issue opening it, right?
No.
Because many people have
No,
issues.
sir.
So what I do now is to, I will maybe send it to people that will not have this, so that it won't look as if I'm forcing people to subscribe. But I will still send it to your mail. But for those of you that are on the platform that subscribe for this thing, it will be there also. You can easily access it through our link, our website. You can access the video there. And it's even more permanent, because sometimes if I send it to your mail now, very soon, by the time you even forget about that mail or delete it, you may not have access to it. But you see it, you just go to the website and just with little amount, just subscribe for the, you can choose the 1 month bouquet there. So you see the video, I will upload the video there. As we finish now, I will upload it so that you can play the video before tomorrow, and if you have questions and ask. But tomorrow will be more excited because we will be discussing regression. It's more of high opening this thing. So I don't know if there's any comment. Any comment? So I will close. Okay, if there's no comment, good night to everybody.
Right, good night to everyone. Good night to you, sir.
Yes, sir.
Right, sir.
Good night, sir.
Okay, good night, sir.
Good night. Yeah, good night.